do a free response type problem. Okay, well, I'll talk about more about that when we get to it. So you're going to have to remind me from yesterday because everyone always leaves off at different spots. I'm pretty sure we were on 41. The question is, did we finish all of the absolute value example?
Yeah.
Yes. Okay. Did we start the square root example?
No.
No. Okay. So we picked up in a good, or we left off in a good spot. So let's take a look at the bottom. Very similar to the absolute value that we did yesterday. We're given a graph and an equation, and they're going to ask us about some different function values, and we just want to make sure that we can figure out those values by hand. That way the graph actually confirms them as well. Yes? Yeah. All right, so before we tackle some of these function values in the little blocks, just for practice, let's go ahead and go over some of these transformations. Can we take a look at the equation, identify any changes, and then we'll kind of make sure that this graph makes sense. Okay, we'll try to check out those changes in the picture. Can we identify any movements? Go, Caitlin. Up 3. I like it. Anything else? Good, Lainey?
Left 6.
Left 6, good. It's a plus, but it actually goes left. Good, Elsie? Vertical stretch by 2, so we're making it kind of taller than it normally would be. Yeah?
Is it reflective of the x-axis?
X-axis flip, good, negative on the outside. Okay, so let's see if this graph makes sense. The beginning point on a square root is normally at the origin. Notice how this one moved left 6, up 3, just like we said. Okay, so that's checking out. The graph, instead of looking like this, like a typical square root does, notice how it was flipped upside down. Okay, because it's going down now. So there's that x-axis flip. The vertical stretch is the tricky part to kind of visualize on the graph. If you were to take the beginning point and then find the next easy close point, when I say easy, I mean like right in between the crosshairs on a graph. If you were to calculate the slope between those 2 points, notice how it would be a value of 2. I know when you see that slope, you think -2 because you're going down, but we're just taking a look at that rise. Okay, how far high do you have to go to get to the other point? So it looks like the transformations are checking out. So graphically, those make sense. Let's talk about these function values. Do they make sense? When you see h of -1, what do you think to do? Or you can ask yourself, what does that -1 represent? I'm hoping at this point it's like intuitively ingrained into you. When you see that, what do you do? Crying is not an option. Go ahead, Lainey. It's an x value. Okay, so x value of -1. Now, before we actually do that, let's kind of anticipate perhaps what our answer should be. So based off the graph, if we go to the x value of -1, notice how the y value on the graph isn't exactly anything, I don't want to say nice, because all numbers are nice, but it's not, bless you, it's not easily identifiable. Okay, it's something between -1 and -2. So we can anticipate what our answer should be. Let's see if we can actually figure it out by hand. So we have the equation. Let's go ahead and plug in -1 just to see what we get. So we'll have -2 times the square root of 5 plus 3. That's as far as we can go by hand. Okay, maybe some of you know what the square root of 5 is off the top of your heads. I don't. More power to you if you do. But if you have a calculator in front of you, go ahead and type it in, and let's see if the decimal value is hopefully between -1 and -2. Yeah. Is there only one over there? Or?
It's 2.2.
We're good? Bless you. Anybody get it? We're hoping negative. Something between -1 and -2 would be -1 point something. Yeah?
1.472.
472. I like it. Can we get that? Confirmed? All right. So our algebraic work, our plugging and chugging, if you will, matches up with the graph. Okay, our answer is something like we said it should be. Let's try the next one. Very similar notation. So the 10 is an x value. If we looked at the graph, notice how it only goes as far as 4 on the x-axis. So unfortunately, we cannot anticipate what the answer should be. It's up to us to just do it by hand, but I don't think that's asking too much of us to do anyway. So square root of 16 is 4, times -2 is -8, plus 3, -5. Okay. So even though graphically we can't see the point, I would say this kind of makes sense. If you were to extend that graph, it looks like if we went out to -10, it would go down to somewhere around -5. Okay, looks good. What if we switched it up a bit? The notation slightly changed. H of x equals 1 now. What is that telling us to do? Or what does the 1 represent, if you prefer that question? What do you think, Elsie? That's a y value. Okay, so let's take a look at our graph. This time we want a y value of 1. And if we were to go to the actual graph, we would have this point, and it has an x value of -5. So we should anticipate our answer to be -5. Let's see if we can actually get that by hand. So if it's a y value, we'll set the equation equal to 1 and try to figure out x from there. So there's a lot going on though. How do you want to start to get that x all by itself? Go, Julia. Subtract 3. All right, so that'll give us -2. Let's keep chipping away. What do you want to move next? Want to keep going? Yeah. Divide the -2. So we'll actually be back to 1. Can we keep going? You're on a roll. Square both sides. All right, so if you square a square root, those are inverse operations. They undo each other. So we're just left with x plus 6. If you square 1, still 1. So then lastly, we can subtract the 6 and we'll get the -5 like we said we should get, okay, based off the graph. We have this connection or relationship. Let's try the next one. Very similar notation. So the -3 is a y value. If we go there on the graph, try to find the point, looks like the x value would be 3. So let's make sure we can get that answer by hand. So very similar, oh, it should be -3. Very similar algebraic steps here, like we did previously. We shall subtract the 3, divide the -2, square both sides, and then subtract the 6. Checking out, the graph's confirming our work's confirming the graph, we have this relationship, everything's good. We doing okay? So far? All right, let's go ahead and flip to the back. We're going to check out our first kind of free response question, if you will. We're going to see many of these this year, and even though we're going to do this one together, you will eventually be doing these on your own, okay, kind of in little groups. You will also see one of these types of questions on every quiz and test that we do this year. So these free response questions, I don't want to say they're difficult, I don't want to say they're involved, but they're thinkers, okay? And how they kind of operate is you're usually always given some piece of information at the top. Okay, some given equation, numbers, information, whatever it might be. And what we're going to do is use that information to answer the various questions that come afterwards. So it might not just be one question or two questions, sometimes it's 3, sometimes it's 4, maybe 5. But whatever's given to you at the top, we can use for every question if needed. Okay, so we always have to be referring back to the top to see what it said or what it told us. Let's take a look at the first one, or let's read the directions. That might be a good first step. Consider the piecewise function below to answer the following questions. So 3 pieces, absolute value, line, quadratic. We got a mixture of things going on here. Check out A. Find P of -3. So here's that function notation again. When we did the square root example before, we said that that -3 in this case would represent an x value. So we want to try to plug in -3 and see what we get out. The question is, we have 3 equations to work with. How do we know which one to plug it into? Because you don't plug it into all 3 of them. It wouldn't be a function then. One thing in, one thing out. What do you think, Travis?
Whichever one has -3 included in the second.
In the setup. Okay, so we're going to use that word domain again. Domain means x values, okay, that work, that you can plug in, that get a point. So that's what's going on this side of the piecewise function. You always have the actual equations, but then they tell you a domain. Okay, where do those equations actually show up? So when we take a look at these 3 separate domains, if you will, which one of them includes the x value of -3? What do you think, Blair?
None.
Why?
Because there's no equals.
There's no bar. There's no equals. So if you take a look at the first 2, notice how both of them have the number -3, but we got to take a look at, can we actually include that? Can we be that number? And Blair noticed how on either of those inequalities, neither one of them has that bar. And clearly -3 is not between 3 and 8, so that definitely doesn't work for the last one. So if it doesn't work for any of them, what do you think our result would be? If we can't plug it in. No solution, doesn't exist, undefined, one of those terms. Okay, maybe we'll just do undefined. Now, notice how the directions for part A also say if a value does not exist, explain why. All right, and this is when your justification might be a little different than your neighbors, okay, or someone around you. So as long as you can explain why there's no value, that's what I'm looking for. So maybe just in general, we can say because the x value of -3 is not a part of any domain. Okay, -3 is not included in any of those 3 pieces. Now they do ask us to find another value. Okay, they want us to find P of 4. So again, we got to ask ourselves, which one equation could we possibly plug in for? Take a look at the domains, the x values, to kind of help you make your pick. Can you find it good, Hadley? How'd you know? There you go. 4 is between 3 and 8. So notice how that x value works. We'll go ahead and plug it into that third piece. All right, so 4 minus 5, -1. Square it. You get +1 minus 5, -4. Not too bad. We doing okay? Let's go on to another question. Okay, so relating back to the top, they're probably going to ask us something about this information. So part B says sketch an accurate graph on the grid. Okay, so piecewise function, we did these previously. We're going to try to get a picture of these different types of graphs. So again, you can go about these any way you'd like, as long as you can graph them. That's all I'm concerned with. But we'll go over some strategies that you might want to use to your advantage. Take a look at the equations. Ask yourself, what do the parent graphs look like? So if the first one's an absolute value, what shape of graph should we be anticipating? Value, yes ma'am. A V. Okay, so a parent function looks like a V. We got to ask ourselves, does it still look like that V, or is there some type of transformation that would change the shape? Change the way it looks? Can you take a look at the equation and identify some transformations? What do you think, Olivia? Say it again? Okay, so up 7. So if we took a V and moved it up 7, it's still a V. Okay, so it still looks like this. We're also moving it left 6, right? So if you move it left 6, it still looks like a V. What else are we doing? Yes? Vertical stretch by 2. So that would change the slope. If you stretch it, it's going to make it a little narrower. It's going to go taller. Okay, it's still a V though. Anything else? Good, Noah? Flip over the X. So, boom, right? Upside down V. So now it looks like that. Okay, so it looked like a regular V for all those other transformations, but notice how the flip actually changes the way it looks a little bit. Okay, now it's upside down. The next piece is a line. Positive slope means it's going to go up. And the next equation is a parabola, okay, a U shape. So we got to ask ourselves, are there any transformations that would change that U? It's moving down 5 and right 5, but notice how it's still a U. Okay, so it's still going upwards. So now that we have the basic shapes, we should be anticipating those on our grid. Let's go ahead and section off our pieces based off the domains. So -8. And then -3, +3, and +8. Okay. You can label 1, 2, and 3 so you know which equation shows up where. And we did not label the outsides, so if you want to cross those out or write none at the top, we shouldn't have any graph there. All right, setting ourselves up for success. We haven't even plotted a single point yet, but at least we are starting to see kind of what should be going on. So let's actually start plotting some points though. We'll start with the absolute value. Let's go ahead and plug in -8 for x. Let's see, +6 would be -2. Absolute value changes it to +2 times -2 would be -4. +7, we get 3. Okay. So plug in -8, get out 3, ask ourselves, open or close circle? Close, right, we have that bar. Let's do the next domain value. We'll plug in -3. +6 is +3. Absolute value doesn't change anything. Times -2 would be -6. +7, we get 1. Plug in -3, get out 1, ask ourselves, open or closed? We got open. So we know that we need an upside down V connecting those two spots that we just plotted. Perhaps finding the top of the V would be beneficial. That way we can just draw our lines from there. Can we take a look at where that vertex would be located? What transformations did we say were there? How would that vertex be moved? We said left 6 and up 7. So if it starts at the origin, moving left 6, up 7, we're somewhere right there. So we'll play connect the dots, making our V shape going upside down. If you wanted to just pick random points, okay, and start plugging those in, that's okay too. but sometimes utilizing those transformations might be a little shortcut, okay, where we can figure out one actual concrete point to use. Let's try the next one. So we have a line. We'll plug in -3 times a third would be -1, minus 2 is -3. So plug in -3, get out -3, ask ourselves open or closed. We got open. Next domain value, plug in +3 times a third would be 1, minus 2, we get -1. Plug in 3, get out -1, ask ourselves open or closed. That one would be closed. So we got to connect the dots, making a straight line. That's not too bad, we can do that. Alright, last piece is our parabola. If we plug in 3, minus 2 would be minus 5 would be -2. Square it, we get 4. Minus 5, we get -1. So we're actually on the same circle we plotted previously. But notice how according to this, we needed an open circle. But there's already a closed circle there. So what do you think we got to do? Or what do you think that means? What would it look like? If you start with a closed circle and then you put an open one on top of it, what does it look like? Still closed, right? Okay, so even though according to this function it has an open circle there, we have the previous closed circle that's filling it in. Okay, so this is going to remain a closed circle. Let's try the next one. If we plug in 8 minus 5, 3, square it, 9, minus 5, we get 4. So plug in 8, get out 4, ask ourselves open or closed, and we got open. Okay, so we have to play connect the dots, but making a U shape. Perhaps finding that vertex would be beneficial. We said based off the transformations, it moved right 5 and then down 5. So from the origin where it normally starts, right 5, down 5, somewhere right there. So we'll connect our dots, making our U-shape graph. I say we're pretty good. Are we starting to get the use of these piecewise functions? Whether you do kind of my thought process or your own, we can get that graph. Perfect. All right, let's try the next question. Explain how the graph in part B, okay, so what we just did, validates or confirms what we did in part A. So in part A, we said that the x value of -3 was undefined and the x value of 4 was -4. How does this graph confirm what we did? What do you think, Noah? All right, so if you go to the x value of -3, notice how when we graphed it, we only had open circles there. There's no closed circle, there's no actual point. So we can say p of -3 is undefined because there are only open circles at the x value of -3. Okay, again, you can say whatever you want. It's your justification. As long as you can effectively and thoroughly communicate what your thought process is or what your reasoning is, that's what I'm looking for. What about the other one we did? P of 4. How does our graph validate this answer? P of 4 equals -4 because... How is this result showing up on our graph? What do you think, Travis?
In the parabola, you can see the 4 value of 4x is -4.
There we go. We have an actual coordinate point, okay, confirming that that result we got by hand is true. It's there. Now, we didn't actually calculate that point ourselves because we just generally drew the parabola, but notice how it's pretty darn close. Okay, it looks like it should be there. So P of 4 equals negative 4 because the point 4 comma negative 4 is on the parabola or on the graph. Again, connection. Our work validates the graph validates the work. Okay, the algebra, the computations. Last but not least, we're going to check out domain and range. And we did this a little bit yesterday on the homework problem, which was kind of an involved graph. This is another involved graph, so this is going to be good practice. But we will be doing more of these throughout the unit, so if it's still a little rusty, don't be too worried about that. So domain for x's, range for y's. We're going to start dragging our pencil to see or ask ourselves where do this graph begin and start, or begin or end. So if we look on the left-hand side, we got to ask ourselves where does the graph start? We're looking for x values. What do you think, Lainey? Negative 8. Can we include negative 8? Do we actually have a physical point there? Yes. So we'll use a bracket. If we continue to drag our pencil, we have to ask ourselves, when do we come to an x value that does not have a point on the graph? What do you think, Hadley? Negative 3. At negative 3, we only have those open circles, like we said in part C even. All right, so we'll have to stop at negative 3. And if we only have open circles there, that would be a parenthesis. Okay, you cannot include that value. Clearly, we have more graph to trace, so we'll throw in the U. Now, right now, our pencil's at negative 3, and the graph continues directly after that. So we'll pick up, or we'll start our new interval at negative 3. As we continue to drag, we got to ask ourselves, where does the graph stop? Or, when do we come to another x value that did not have a point? Can we find it? 8. Good. Okay, somewhere at the very end. And it had an open circle there, so just use a parenthesis. Now, if we end at 8, we don't have any more graph to actually trace, so there's our domain. We actually have 2 intervals, or 2 chunks. Yes?
So are the points that you have to put down, are they just where open circles are?
Yes. Or wait, you mean these ones?
Yeah.
Those are open circles. Yeah, so open circle at negative 3, open circle at 8.
So you don't have to put down where there's closed circles?
No, because closed circles are telling us that that x value works. You are able to plug it in. So we're just concerned for x values that don't work. That's where we're going to write the like the beginning and ending points. Okay. Yeah.
If there's a x value that, like, if not like the one that we have here, which is with the pivots or both, but like what if they're on like separate y levels, but the x value has at least one closed, then you can continue it through, or we just stop the graph.
Great question. All right, so I think Travis is asking, what if we had a graph that looked like this, and this was like at the x value, we'll say a 4. Okay, so if you drag your pencil across, we have a graph here, and the moment you get to 4, you got to ask yourself, can you include that x value? Yes. You cannot include it here, but you can include it there. You don't have to make a break. Nope, you're just going to keep dragging your pencil. Okay, we're actually going to see that, though, when we do the range. So that was a very, very good question. Let's check out the range, though. So this time we'll go low to high. We got to ask ourselves, where does the graph start? Look at y values. Looks like negative 5. Is that what you're going to say, Maggie? Okay, so that's the vertex of our parabola. It has a closed circle, so that would be a bracket. Now, as we continue to drag our pencil up, notice how we encounter an open circle at the y value of negative 3. But very similarly to what Travis was just asking, he was wondering, what if you also have a closed circle at that same spot? So even though we have an open circle here, we do have closed circles on the graph at some other location. So we do not have to break or skip over -3 because that y value does exist. It exists over here, just not here. So as long as it exists, we're going to keep dragging our pencil. All right, so if we keep dragging, we encounter another open circle at 1, but again, that y value does exist somewhere else. So we're going to keep dragging our pencil. We have another open circle at 4, but that y value exists somewhere else. So we're going to keep dragging our pencil. It looks like we're going to keep dragging it until it actually ends, which is the height of, what is that, 7? And that has a closed circle, so that would be a bracket. So when you're dragging your pencil left or right or up and down, you're just concerned with where there is absolutely no graph. Okay, no graph, no closed circle, there's nothing. So as long as there is a graph, you're just going to keep dragging your pencil, whether there's an open circle there or not. Okay, again, kind of involved, but we're going to start to see more of those as we go. How'd you do on your first free response question? You think you would have done iffy, okay, if it was all by yourself? Maybe. Okay, we're going to build up some confidence with these as the year goes on. Okay, but eventually you will be doing them on your own. We'll stop there for today, and we'll save the next section for tomorrow.